Allow me to share my screen. What you can view now is the slide covering the topic on non-homogeneous higher order differential equations solved using the method of undetermined coefficients. So we discussed that if you are using the method of undetermined coefficients, you have restrictions to it. And the restriction is based on the function of x that you see on the right side of your equation. So if you have functions like tangent, hyperbolic functions, inverse hyperbolic functions, inverse trigonometric functions, the natural and the common logarithmic functions, they cannot anymore be handled by the method of undetermined coefficients because our g of x here is limited only to polynomials, constant, exponential function, sine and cosine, or the combination of this. So other than those functions, this method will not work already. And we also discussed that your solution for under the method of undetermined coefficient will have two parts. One part will determine the complementary equation, which is exactly the same as determining the general solution for a homogeneous higher order DE. So in there, you get the roots of the characteristic equation, and the roots tell you what would be the corresponding functions that should appear in the complementary solution. Now, aside from the complementary solution, you have the particular solution, which this time is dependent on the g of x. So you were given examples on this. So the first example gave you a constant, which is so easy because in terms of its form, so it's only the form, you have the right side of the particular solution equated to an arbitrary constant here. So the letter that you're using is randomly selected, so you can choose the letter that you want to represent it with, primarily because it has no significance, since anyway you will determine its value. So what you do with the form of the particular solution, you differentiate it depending on the number of derivatives that are present on the left side, because you're going to substitute it there. Okay, so substituting the derivatives of your unknown function and its form in here on the left side of the DE will give you a value of -8 for the A, telling you that your particular solution is -8. So what you do, you simply add the complementary solution and the particular solution. So this is always the case with the method of undetermined coefficients. So we have the second example as a polynomial. So I will not go through anymore the process of finding the roots, because that's discussed already in the method of under the homogeneous DE topic. Now here, your particular solution, since you have an x squared on the right side, will be having this form. So this is the form, a second degree polynomial. You're differentiating it as well, and the derivatives and this form substituted to the original, giving you this. And this is where you use equating coefficients to determine the values of A, B, and C. Okay, the same procedure that was used in your integral calculus under the method of partial fractions. So after you have found the values of A, B, and C, you go back to the form and substitute that value. And then you add it to the complementary solution. So that's in the case of your g of x, which is a polynomial. The third is a sine function, which could also be a cosine or both the sine and cosine, provided that they have the same argument. So the form of the particular solution is this. Okay, and you're going to differentiate it also. Substitute it in the original DE. This time you equate coefficients of sine and cosine, not x squared, not x, and not constants. And in here, you determine the values of A and B using the methods of your algebra. And this is the value of A and B. So if you know that, you substitute it on the form that you have written, and you add it to the YC. That will give you the complete solution of your non-homogeneous DE. So you add the two, that would give you the complete solution. There are instances wherein you also have exponential function on the right. So if it's an exponential function, this is the form of the particular solution. Okay, so you differentiate it, in this case twice, because you have also until the second derivative. Substitute it in the original DE, that way you get to find the A. Once you have the A, then you get to know the YP, because it shouldn't contain any arbitrary constant, and you add it to the YC. Okay, your YC is needing you to determine the roots of this auxiliary equation. Now the roots are 4 and -1, so this is your complementary solution. There was an error in the independent variable because it should be t, because your independent variable here is t. And then you get the sum of YC and YP to get you Y, the complete solution of your DE. Okay, I'm just going through this fast because we have covered this already. There are cases wherein you have products. This one is a product of a cosine and a polynomial. So take note of the form of the particular solution. So what you have here is the cosine and sine pair, initially because of the cosine 3x here. But you replace the A and B in the form of a cosine function by the form of the particular solution of this x here, which is ax plus b. But you're not allowed to write it here as ax plus b as well, because this constant is different than this. So you write here cx plus d. Okay, that's the form. Now, how you're going to find A, B, C, D in here? The same as the previous examples, only that this one really would require really a long procedure, because your process of differentiation is long. Okay, you will do differentiation or the product rule of differentiation here. So since you have until the second derivative, I think you know that it would really be very long. Now, the example that was used is in here. Sample 5 is the product of an exponential function and a cosine. So the form of the particular solution is based primarily on the cosine. But since you have it multiplied by e raised to 2x, you have it here appearing. But you don't add anymore another constant here. Okay, the constants, the arbitrary constants appear on the cosine and the sine. And you do the same procedure as what was done in the first 4 examples. Now, your YC in here is e raised to 2x, c sub 1 cosine 3x plus c sub 2 sine of 3x. Look very closely. E raised to 2x, c sub 1 cosine 3x, and c sub 2 sine of 3x. You have the exponential function e raised to 2x, and you have the cosine and the sine function in your YC. The YC is based on the auxiliary equation. Okay, the auxiliary equation, I'd like to go back based on what is written on the left side. Okay, now what will happen, since in terms of the form, this is your YP and this is your YC. In terms of form, they are exactly the same. They only differ in the constants here, c sub 1 and c sub 2. Now in YP, we write it as capital A and capital letter B. So it's similar in form to YP. So what would you do, since your YC, your complementary equation, is similar in form to YP? You will modify the YP. So there's a need for you to modify the YP. And just in case this was not emphasized last meeting, so you modify the YP by multiplying it with the X or the independent variable. That way it will not be similar to this in terms of form. So you have the X in here. Now, if you do differentiation now of this particular type of YP, because it's the YP that we differentiate so that we can find the A and the B, you see the challenge in here that you will do double use of product rule of differentiation. Because if you consider this as your first term and this as your second term, your product rule of differentiation will be applied to this. Okay, first term times the derivative of the second plus this second term times the derivative of the first. The problem with the first term that you have selected is that it's in itself also requiring a product rule. So the derivative of this in the second term of the differentiation of this entire expression will be using product rule as well. So it's really, really, really very challenging to go over or to do it, to do the process of using the product rule of differentiation, especially if the form of the differential equation will require that your particular solution be written in this manner. So that's the purpose of the topic that I'm going to discuss in a little while. Okay, but nonetheless, in here, you see that there was no exact answer that is written here. So we will modify the, or we will find the answer to this expression later once it's modified using exponential shift. Now you can have this one as well. Okay, x and cosine x. So this is your complementary solution. You have these auxiliary roots. I think you know how to find that, and the homogeneous DE. Your g of x is x cosine x. So cosine and sine in here, but you change the a and the b by the ax plus b and cx plus d. The form of the particular solution of the x in here. So when you do differentiation, this is the one that was presented to you at the start of the products of functions for g of x in this set of slides. So this is your first derivative and this is your second derivative. All of these expressions, I think, were already simplified. Then you substitute it on the original DE here. Okay, and equate. So if I have not emphasized it again, when you do equating coefficients here, you can start equating coefficients of the two trigonometric functions, sine and cosine. So you do it first with the cosine. So this is it. From this particular equation, you do another process of equating coefficients. That's for the terms that has the x and the constants. So it will give you this particular equation and this particular equation. You can solve anything because you have 4 unknowns. So you need 2 more. So from the sine of 3x, you'll have this equation. From this equation, equate coefficients for x and constants, you have this. So using your algebra, find A, B, C, D, using the 4 equations for unknowns process. So you get to find A, B, C, D. Okay, this YC here we determine first, and we add the YP in here after we have determined already the constants. Okay. Now, in cases wherein you have a combination of functions, I've mentioned this already. If you have a combination of functions, you have to set up 3 different differential equations for each of the functions. So one for the right side, 3e raised to tx only, 2t rather, and then the second one has this, and the third one has this one. In terms of YC, they all have the same YC. So they will just differ in the YP. So you add all the YPs for these 3 different forms of your DE to the one YC because they have the same left side. That would then be the complete solution of your given DE. So in this case, class, this is your answer in this case. Your exponential function is this, your sine and cosine is this, and your e raised to t cosine 2t with this negative 8 constant is this pair here. This is your YP. Of course, you still need to find the YC, which is very easy based on the roots of your auxiliary equation on the left side. So far, these are the things that you have learned using the method of undetermined coefficients. So just don't forget, if I fail to emphasize the modification of the particular solution, if the form of the complementary solution is similar to that of the particular solution, it's the particular solution that you modified. So originally, your particular solution doesn't have the x here. Amo lang ni siya. Okay, that's your particular solution. So what you do, You modify it by multiplying it with the independent variable so that you'll be able to find your constants here. So I'd like to start this afternoon with g of x for non-homogeneous DE, which has an exponential function on the right side, like this one. It has an exponential function because, let me go back to the DE, you have this. This could be solved easily without having to worry about the length or the time that you will take to finish the solution of such a problem. So in this case, we will solve a particular DE in here using exponential shift. So exponential shift, so I will introduce it now to you. Exponential shift requires that your g of x on the right side has an exponential function. So if the other examples here or the examples covered here has restrictions already because the g of x is limited to the functions that you see on the right side, this one is even more specific as to the limitation, the restriction. The right side has to contain an exponential function. Okay? But before I give you an example on how to use exponential shift in simplifying solutions of this type of DE, e raised to 2x cosine 3x, or e raised to 2x, for example, times the quantity x cubed plus 1, something like that. So it has an exponential function on the right side. Do you have any questions so far here or point of clarification on the topics we have covered? And actually, you have taken the quiz already. You have any questions? None? Okay. I'll open Jamboard. Class, ha? Wait lang, class. Let me share again my screen. Okay, we'll start with this example using exponential shift. You can still solve this based on the topics we have covered already. So you will just write the form of the particular solution for this one based on the third degree polynomial here. So you will write ax cubed plus bx squared plus cx plus d. And you will multiply it, of course, with the exponential function e raised to 3x. That's what you've learned. Okay? In this case, you need to differentiate it thrice, 3 times, because, oh no, sorry, twice only, because I only have written here until the second derivative. So this d, by the way, I have discussed this already during the homogeneous DE topic, that it represents in shorthand manner the derivative of your unknown function. So this is the second derivative of y with respect to x, the first derivative of y with respect to x, and this is constant 5. Now, we will use, in this case, exponential shift for this particular type of DE, this one, the original one. So what we do, so I just wrote in here the form of the particular solution if you're just using the method of undetermined coefficients. So I'd like to write the acronym MUC, method of undetermined coefficient. Now this time, we will tackle or solve the DE using exponential shift. From the term exponential shift class, you will transfer this exponential function on the left side. So if you transfer it, that would be e. So the only way that you can transfer it is you divide by e raised to 3x, right? So the e raised to 3x, if it goes up, it would be e raised to minus 3x. And you copy. This would be 16x cubed. So you could see that the original right side, which would result to this particular solution, is now simplified. You only have 16x cubed left here. So meaning, if I write its form of the particular solution, it would be simply like this. No more exponential function attached to it or multiplied to it. So that's the purpose of exponential shift. It is used in handling non-homogeneous differential equations in which the right side constitutes the product of an exponential function to any of the polynomial sine or cosine function. You simplify the form of its particular solution if you're using this particular method. However, class, you see that if you have changed the left side in this form, there has to be a treatment of this. Okay, how do you then treat this particular expression of e raised to negative 3x times the quantity d squared minus 2d plus 5? Now, you will apply a formula for this, a particular expression in which you have transferred the exponential function from the right to the left. Now, what is the formula? So it would be something like this. So I'll first write the f of d minus a. Or I'll write it here on the right side na lang. So you will see the result on the right side. So what you have here on the left is, this is your e raised to ax. And this is your f of d. And that's your y. So I aligned them so you could see. And how do you treat it? Not that it should be equated to this one, but this is to be interpreted in terms of exponential shift as, or this should be transformed in terms of exponential shift as f of d minus a times a new unknown function which constitutes e raised to ax y. Now, how should you interpret this particular thing here? Whenever you have this expression in your particular DE, like this one, it's e raised to negative 3x, meaning your a here is negative 3. Okay, so you would understand better. Your f of d is just the function of d, the function of the differential operator d. That represents this d squared minus 2d plus 5. And this is your y. So if I place an arrow, it's actually like that. Okay? Now, how will you treat this particular expression if you're talking about exponential shift? It should be treated this way. The d's that you see here, the operator d's that you see in your f of d should be shifted by subtracting from the d's only, the value of the a, and then your unknown function originally, which is just y, is now changed to a new unknown function, which constitute, or a hybrid, like to use the term, a hybrid unknown function, which constitute the product of your exponential function and your original unknown function y. Now, to illustrate what I mean is this. So I will now change this left side based on this formula. So the treatment would be this. So this d here would be d, so it's minus a. F of d minus a. Only the d's will be shifted by subtracting from it the a. The a is negative 3, as I have mentioned a while ago. So d minus minus 3 is d plus 3. Now, since this d is squared, so you also square it here. Copy minus 2, you see another d. So it should be d minus a. So d minus minus 3. So that should be plus 3. Now that 5 doesn't have a d, right? So you just simply copy it. Now this expression now that I have done is equivalent to this, the f of d minus a. your unknown function hybrid, your new unknown function hybrid would be e raised to, kung ano ang kinhatag, negative 3x y. So this is your unknown function hybrid. You copy what is written on the right side, which is 16x cubed. You get it? The form that you have here on the left, this form that you have here on the left, you have transformed using this formula, applicable only to exponential shift or for this particular condition. The right side, you just simply copy it. Okay? Now, if you will simplify this, you simplify this just using your algebra. So you have this expanded and this expanded and this added. So that will give you the simplified form. So if you will do that, you have d plus 3 squared. So that would be d squared plus 6d plus 9 minus twice of d plus 3. So that would be, I will just simply place it here. So you have minus 2 minus 2d. So minus 6. So that would be minus 2 plus 3. So that would be minus 6. And you have here plus 5. And still copy your hybrid unknown function. And you have here 16x cubed. I hope you can follow what I did. So I just got this one, expanded this. I had this one and this expanded and just multiplied it to this. Very class, wait. Okay. We'll stop sharing. Again, there's something wrong. We'll share again. I click something accidentally, so I cannot change next slide. Kasa? How come I can't share next slide? And okay. Hopefully this will be gone so I can click on next. Okay. Sige. Sorry about that. So you have this. Expanded the left side and you now have this. And if we simplify the left side, we have d squared. A 6d minus 2d is a 4d. A 9 minus 6 is 3 plus 5, that would be 8. And your hybrid unknown function. I wrote already yp here. 16x cubed. Now, I may not write the yp in here initially if you want. So if you're wondering why I wrote the yp there. But if I write the form of the new particular solution in this type of DE now, so you have this case e raised to negative 3x y sub p will have a form of its particular solution as ax cubed plus bx squared plus cx plus d. Okay? You don't only write y, but rather you write now the entire expression here, which is the hybrid. It's if it's just one entity, it's just one thing representing your unknown function. So you have this one. Then you treat this entire thing as one and differentiate it depending on how many derivatives you see here on the left side. So the first derivative, so I'll write it as d. The first derivative of this hybrid unknown function of ours is 3ax squared plus 2bx plus c. The second derivative is equal to 6ax plus 2b. Now what will happen to this? to this and this. It will be substituted in here. The purpose is for you to find the value of A, B, C, and D. Okay? So I'll go to the next slide for that because that would be one lengthy equation. So if we substitute, it would be something like this. We substitute already the three derivatives and the unknown function. So you have d squared here. So that would be this one, 6ax plus 2b. Okay. Then you see you have 4d. So meaning all of this will be multiplied by 4. Okay. All of this should be multiplied by 4. So your answer would be something like this. So just add it in here. So you have 12ax squared plus 8bx plus 4c. So what you did, or what I did, is just simply multiply this one by 4. And since it's 8 times this one, the hybrid unknown function, all of this will be multiplied by 8. So you will have 8ax cubed plus 8bx squared plus 8cx plus 8d. And it should be equated to, so this is just the same as what we have done in method of undetermined coefficient. 16x cubed. 16x cubed. And you just equate coefficients. So it's practical. You start with x cubed. So you will have 8a equal to 16. And a is equal to 2. X squared is, you have here 12a. And you have here 8b. You have nothing here. So that would be 0. So you have 24 is equal to negative 8b. So b is negative 3. Then you can have the x. So for the x, you have 6a plus 8b plus 8c, still 0. We don't have x here. So we have a 12 here as 6 times 2. We have here 8, negative 24 and 8 times negative 3. And might as well transfer it on the right. So negative 8c. So negative 12 is equal to negative 8c. So c is equal to 12 over 8, or that would be 3 over 2. Dividing 12 and 8 by 4. If you'll have x raised to 0, that would be for constants. We have 2b in here. And you have 4c in here and 8b. So you have negative 6 for this one. For a c, that's 12 divided by 2. So that would be 6 plus 8d. So d is equal to 0. You know already A, B, C, D. So what would you do? You go back to the form. Which form would that be? This one. Okay. So from here, I'd like to use a different color. You apply the A, B, C, and D. Okay. So E raised to negative 3x y sub P is equal to, so what's our A? 2B is negative 3. Excuse me. Okay, you have this. What's our C? 3/2. D is 0. If you bring this e raised to negative 3x back here, then we say that our particular solution is e raised to 3x, transferring the e raised to minus 3x on the other side, times the quantity to x cubed minus 3x squared plus 3/2 x. So you see, your particular solution actually is the same in form as the original if you use the pure MUC process. So you already have the e raised to 3x and you have here the representation of your third degree polynomial. In here, we just use the exponential shift. That way, our particular solution form will not be hard to differentiate. So differentiating here is limited to this simple process of differentiation. Whereas if you're going to compare it with the original one, you're going to use product rule of differentiation here. Why? Because this is a different function and you're multiplying it with this polynomial. So you need to use product rule in that case. However, don't forget that this is not yet the end of the method of exponential shift. Of course, you still need to find the YC. So since this is a modified, if I may say, a modified procedure of the method of undetermined coefficient, don't forget that when you determine your complementary solution, it should be based on the original DE, not to this one. So your YC is not based on this. So not based on this, but rather on the original. So this one, if you find the roots of this equation, actually that's not factorable. So the root of your equation is plus minus 2i, if this is your equation. So if it's plus minus 2i, to cut our procedure, your d squared minus 2d plus 5 equal to 0. This is your complementary equation. If you write its auxiliary equation, it would be like this. Finding the roots for this one will use the quadratic equation, and this will be the answer that you will be getting. So your YC in this case will be using this complex pair of roots. So you have e raised to x times the quantity c sub 1 cosine 2x plus c sub 2 sine of 2x. Your complete solution should still be the sum of these two. So e raised to x, c sub 1 cosine 2x plus c sub 2 sine of 2x plus the yp that we got in here. This one. So e raised to 3x and you have 2x cubed minus 3x squared plus 3/2 x. Okay, let me check if my memory is right. 2x cubed minus 3x squared, 2, 3, and 3/2 x. So this one is the complete solution of the set DE using the method of exponential shift. The procedure, if you will ask me, is 80% similar to method of undetermined coefficients. We modified only in this portion here. In here. So from this one, you transfer the exponential function on the left. Now your left side is comparable to this form, and you need to transform this e raised to ax function of dy to this form. So shift by changing only the d, so the constant you don't change, by subtracting from it the a. So it's important that you determine the a correctly. So it's in this case, it's -3. Then simplify. So you have simplified it until you are in this form already. And write the form of the particular solution of your hybrid. So this is your hybrid unknown function based on the formula. Then do differentiate the hybrid of your unknown function based on the DE that you have here. And write the form of its particular solution back in the standard form, not in the hybrid. So this is the hybrid form. Now, how do you return it to standard form? Simply isolate your unknown function on the left, meaning transfer everything other than the unknown function to the right. And then determine still your complementary solution and add the two. Any questions? You have any questions? No more question. Wala gid question. Naintindihan niyo gid? Do you have any question, Kyle, Jim, Marion, Marian? Wala. Sure ka mo ha? Wala ka mo question ha? So you do the same class. For example, I go back here. What if, I'll change to a different color. What if it's not 16x cubed e raised to x here? What if you have a different one? Let's say e raised to 2x sine of x. You do the same thing. Just transfer this one here. So this one becomes e raised, we'll make this negative. So this becomes positive 2x d squared minus 2d plus 5, and you are left, rather y, and you are left with the sign of x here. So when you write your hybrid form of the particular solution, it will only be based on the sign. No need anymore for the exponential. So initiate nyo naman. So this would be d minus 2. This should be d minus 2. This should be e raised to 2x. Y. This should be sine of x. The rest would be the same procedure. Okay? So these are just but the scenarios where you can apply the exponential shift. So it need not be specified that you use it, but if I may suggest, I always do it this way if I know already exponential shift, because if you deal with the original g of x and write its form of the particular solution based on the original, you will have a hard time differentiating. And once you have differentiated already and you'd like to substitute based on your original dA, you have one very long second derivative, first derivative, and the constant here to write. Good if you only have until second derivative. What if you have until third derivatives? You will really have a hard time doing product rule of differentiation to the form of the particular solution of this. Okay? Any questions? The exponential shift is restricted to functions in which, or to g of x in which you have an exponential function. That's the restriction. But it simplifies method of undetermined coefficient for such a function. The next method that I'm going to introduce, because I don't have enough time, the operator method has also a restriction because it's only the last method that does not have the restriction. So the operator method, if I will emphasize, requires that your f of d, the function of d on the left side of your dA, should be factorable. What does that mean, Miss Ali, when it should be factorable? So meaning, you should only get real roots from the auxiliary equation. If you're getting imaginary roots or complex roots, this operator method will not work. Again, it's only limited to higher order differential equations with constant coefficients which have real roots. Hindi pwede sa may imaginary root, hindi pwede sa may complex root. But as to the big question, can it process any g of x expression? Can it process any g of x expression? For example, can it process a tangent a second, a cosecond, an ln x? The answer is yes. The limitation of this method is the one I have mentioned a while ago. It needs that your left side should have constant or real roots, non-imaginary, non-complex. Okay? I'll give you one very simple example before we part ways to give you an idea on what is so likable about the operator method. Majority of the students doesn't like it because they will integrate. Okay, in here, you need to integrate. And it is restricted to factorable function of the expressions. I'll give you one simple example that you can best use in here. Wait now. Okay. Okay, let me try this one. Okay. What if you're given something like this? Isn't this equivalent to the second derivative of y with respect to x? It's just a short way of writing it. And you have 9e raised to 3x here. So in the method of, in the operator method, in the operator method, whenever you see a d here, you transfer it on the right. Okay? How? Just like you're treating it as if it's an x or any variable in algebra. In operator method, your goal always is you isolate your unknown function in the left side. Isolate meaning you get rid of this d. So how do you do it? You will divide the entire expression by this d. So this is how it will look like now. It will be y equal to 9e raised to 3x. And you will have here d squared. It's just you transfer that one in here. This could be written as 1 over d times 1 over d. I'll explain why I have expanded it like that. And I'll place this inside the parenthesis e raised to 3x. Now that one could be treated as this. The number of 1 over this, how many 1 over this you see here on the right side dictates how many times you will integrate the function of x here. So this is your function of x. So the 1 over d tells you how many times you will integrate this. In here, you will have to integrate it twice because you have 2. So what will happen now? How it will look like now? So I'll write it here. Y then is equal to the double integral. I'll place the 9 here. E raised to 3x dx dx. I get rid of the 1 over d because the treatment of this is one integral. The other one is another integral. Of what? Of the function that appears after it. So that is why I'm saying there's no limitation as to the g of x that appears on the right side because anyway, you're going to integrate it. So it depends on you as the one who's using integral if you know how to integrate. So if you integrate this once, you need a 3, right? As the derivative of this, you take it from here. So you will have 3 left here and you will have e raised to 3x and the dx plus c sub 1. Why do I have the c sub 1 here? Because I'm integrating an indefinite integral. So the integral of EU du, I took 1, 3 here, is EU itself. So this one. Integrate it for the last time. So the integral of that will need this 3. So you have e raised to 3x. And this one, if integrated, will now need the variable x. C sub 1, when integrated, I'll place, by the way, dx along outside. So you will see. That thing. So it should be interpreted that way. So e raised to 3x plus c sub 1 dx. So you integrate it for the last time, the second time. So your answer would be e raised to 3x for this. You use the 3 and you have c sub 1x plus another arbitrary constant of integration. And based on the operator method class, this is already your final answer for the answer of this particular TE. So if you want to rewrite it in the form y is equal to, want to write it like c sub 1x plus c sub 2 plus e raised to 3x, fine. But if it's written like that, there is no need to write in particular order, just like in method of undetermined coefficients for your y-C. Okay, so you learned one formula under the operator method, the 1 over d. So if you see an expression here that contains these or expressions of these, as long as they are factorable and they have real roots, transfer it here on the other side. We will deal with examples on roots which are real but does not come in the simplest form as 1 over d only. Okay, I'll give you an example on that on Thursday, before probably 2 more, before we go to the last method, which is the variation of parameters. It's the last method actually, and it's the most versatile because it doesn't have any restriction. Okay? Now, any questions? No more questions?